Can go ahead and get started, and hopefully we get some more folks coming in as we get going. Before we start the talk, I wanted to just kind of introduce this season of Exoplanet talks. This is the first one of the 2020 series, and again, I think I want to thank Professor Leon Ofman here for speaking with us today. I'm going to go ahead and post in chat the link to our website and also our YouTube page, which has the previous recordings, and our website has the upcoming schedule of the talks. And we still have some spots available for the summer and fall. So if you know anyone or you want to give your talk yourself, please feel free to reach out to me. But with that, I want to welcome Professor Leon Ofman. Professor Ofman received his bachelor's and master's in physics from Tel Aviv University, which I believe is where he's speaking to us from today, and his PhD in 1992 from the University of Texas at Austin. And since receiving his PhD, he has been a researcher at Goddard in a number of different roles. And since 2009, Leon is a research professor at Catholic University. And his main research interests are in solar and space plasma physics, but he recently became involved with exoplanet research, particularly when it comes to machine learning, which I believe we will be hearing about today. So Professor Ofman, I'll turn it over to you, and thanks again for coming out and talking to us today.
Thank you for the introduction. Can you hear me?
Yep, good, loud and clear, and I can see your
slides.
So
I'm going to talk today about automated detection of exoplanets in TESS data. This work was done in a collaboration with Professor Auerbach at Tel Aviv University Maths Department, as well as people at the Theta Ray company. It's that develops the machine learning software. So first, and I would like to acknowledge collaboration and discussion with Professor Shai Zucker and Tzvi Mazet, Tel Aviv University, on this topic. So first, a couple of sentences of sort of disclaimer. I've been working in solar, in heliophysics, and that's what I've done for most of my sort of career in the field. And but recently, I became interested in exoplanets, and especially, as Joe mentioned, in the automated detection using machine learning. So that's what I'm going to talk about right now. I will also give you some overview, some introduction on this topic for, if there are students or people that are listening that are not, haven't been working in this field before. So it's a relatively new field that has started in about 3 decades. And if you think about it, in '92, when I was just graduating with my PhD, before '92, there were no known exoplanets. And today we have more than 5,000. I think recently NASA announced that we passed the 5,000 exoplanets mark. So obviously, of particular interest are habitable exoplanets that are Earth-like, but so far only a small fraction have been identified. There are about 60 that are, maybe 20 of them are Earth-size, and then the rest are sort of super Earths. They're larger, but still are in potentially habitable. So transiting exoplanet search is one of the main methods. The other method is Doppler velocity measurements. It's basically detecting the wobble of the star that is orbited by the planet. And there were quite a few dedicated missions, if you think about it, that were launched to search for exoplanets. And there is a list here, as you can see. Even the recently launched James Webb, one of his goals is to study exoplanets. So, and there are future missions as well. Most of them, or all of them, are NASA and ESA missions in this list. I'm going to focus on Kepler and TESS. Okay, and there are large data sets of tens of thousands of light curves collected over several years that need to be analyzed. And we're talking about a signal that has very low signal to noise, and there could be some issues in the processing that makes it difficult. So when you have such a large number of curves, you are looking only for small signal, then one of the recently emerging methods is to use AI and machine learning. And the implementation of these methods is increasing. So for example, you have, I'm going to discuss in some detail the Chalou and Vanderburg paper, and there's the Thiele et al. And of course, our most recent work that was published recently. So I'm going to talk about some results and present the results of our study. So basically, as a solar physicist, of course, I'm interested in the examples we have in our solar system. And we do have a couple of transiting exoplanets, not exoplanets, they are planets in our solar system, but they're between us and the sun, so they can transit when viewed from Earth. So the interesting thing is to see the complexity of the stellar surface, and in this case is the sun, which we don't have in normally in stellar observations. And you can see that, for example, in extreme ultraviolet here, we see the complexity of the emission and the effect of the solar, the transit of Venus in this case. So obviously the Venus has to come between us and the sun in the line of sight, and this happened in June 5th, 2012. So you would think that Venus is quite close, so it should happen quite often, but actually these transits occur in pairs and then they don't occur again for another about 100 years. So this shows the transit of Venus as recorded by the Solar Dynamics Observatory, which looks at the sun at various wavelengths, invisible and extreme ultraviolet. And you can see that, for example, this is a helium emission. If you would look in helium emission, it will be very difficult to see the signal because of the variability of the solar emission. Okay, so this just to show you what we are dealing with in various wavelengths. But of course, most of the observations from TESS are in visible light, so we don't have to worry maybe about variability in visible light, except for in this case sunspots or star spots in other stars. So to move on, you can see that the next transit is going to be in 2117 on December 11th. Maybe it's too soon to mark the calendar, but still. So if you're talking about Mercury, of course, Mercury has many more transits because it's closer to the sun, and it occurs maybe a couple of every decade or so, but then they you can see that it's much smaller, so the signal would be much more difficult to detect. So clearly you would need a special orientation for the exoplanets to be detected. They have to be in the line of sight, so that would already exclude many exoplanets from our view from the Earth and only select those cases where they are transited in front of us. So we're dealing with a very weak signal for most of the cases. And you can see here, this is the relative intensity on the right, and it goes down by only a couple of percent. But if we have star spots similar to the sunspot, then there could be additional non-planetary variability, and then there are many other sources of noise. For example, if the emission is not uniform, you can see a lot of scatter, and there could be just the photon shot noise, as you don't have too many photons coming from that star. So this is the residual you can see in the lower panel. So one thing is that because of the signal is so weak, it would be a sort of a nightmare to observe it from Earth because of our atmospheric seeing that would add to the variability of the signal and to the error bars. So then the Kepler mission was one of the first dedicated missions to study exoplanets. And I'm going to discuss how we used Kepler data in our study. So basically, in the first phase of that mission, it observed a region in the sky with a 1 meter optical telescope, and it monitored 200,000 stars for 4 years. So there is a lot of data that needed to be automatically analyzed, and that was done as well. So from the archive, from the NASA Exoplanet archive, we see that this was from 2018. This graph, it's only had about half of known exoplanets that we have today. But you can see that Earth-sized planets that orbit their stars with the same period as Earth of about 365 days, there is only a small number of these planets. And you can see this, the red line, the lower red line, marks the Earth radius, okay? And the upper one is 4 Earth radii, sort of arbitrary, giving us the possibly habitable planets where the gravity is still sort of bearable, okay? And also, if you look at longer periods, of course, you detect less of these stars. So now this is a schematic view that shows the exoplanets on the background of their host stars. And they are also ranked by their spectral class, okay? So you can see the whole variety of exoplanets that's known today. Some of the systems, there were more than one exoplanet discovered in the same star. So because we have such a large data set of curves, light curves, we would like to apply machine learning methods. And this was done by Shalou and Vanderberg. There were also other studies in 2018 where they applied neural networks to classify light curves from Kepler data. And you can see here, what is shown here is the classification of the whole time series, okay, which is called the global view, showing the dip due to the exoplanet, transiting exoplanet. And here is the local view when the data is face folded, basically taking, maybe they were observed several such transits, so they are all face folded into one. So they use both the global view and the local view as input into the neural network. Now, this is the connected neural network where you have the input layer, and then there are the hidden layers and the output layer. And they also tried different types of neural network. They tried the convolutional neural network, where they also look for translational invariance in the data set to improve the classification. This method is often used in image processing. So that gives sort of better results. So in that study, they used label data. So they actually specified for each in the matrix that they get for each column, what is the label for this data. And they trained the neural networks using human classified Kepler threshold crossing events. Okay, with this approach, they got 98.8% of the time they ranked planet signal higher than the false positive signals. Of course, you have to understand that we are talking already about threshold crossing events. So they already been selected by the Autoencoder and as a threshold crossing, and then the algorithm takes all these still large number of light curve and ranks them. And then what they found that it improves the ranking of the true planets versus false positive. So then they were able to validate statistically 2 new exoplanets that were identified with higher confidence than others. Okay, so Dattilo et al. In 2019 used the K2 for data analysis, which was the second phase of the Kepler mission, where it already couldn't point to a specific point, but mapped different parts of the sky. So the light curves needed to be analyzed in more steps. So, but here is the description of this is, for example, a light curve that has some evidence of transits, and then it's flattened, and then you see the zoom in the local view of the transit when they fit. So basically, it's called a box least square fit. They fit this curve, and then this is the residual. Okay, so that was then given as input, okay, to the neural networks as machine learning, and then they used it to classify the light curves. But they were sort of prepared manually. Okay. Now we are talking about the TESS mission, okay, that monitors 200,000 stars. And we can see that, again, it scans the sky, and you can see that it takes quite a while to map the whole sky. But the interesting thing is that in this region, it will overlap with James Webb. So this is of interest when now we're starting to receive the first images from James Webb. So that would be interesting to see in the same stars where exoplanets are identified by both missions. So this was the first 3-planet discovery that was published in January 2019, and we are a little bit over than the 3 years now. So now we have already more than 15,000 threshold crossing events, okay? And they need to be, of course, classified. So you can see that there are 172 confirmed TESS planets, but there is also 1,075 false positives, and about 1,081 TESS objects of interest with a radius that are less than 4 solar radii, not solar, sorry, Earth radii. So what you see here that, you know, we start with 15,000 and we need to get to 172. So manually, it is a big job. So for those of you, TESS objects of interest is just it's not necessarily a planet, it's a planet candidate, and it could be just a single transit, or it could be some other astrophysical target, but that is where we need to classify and to get into, at least from TCE to TOI. Okay, so now this is the pipeline of the data, that you can see here that the flow chart from the observatory. The data are collected by the Deep Space Network, and then it goes to the Science Operation Center, where it's then processed, and then it goes to the science office, and then finally it gets to MAST, where it's archived, and then this data is the data used in the analysis. Okay, so now just to summarize the deep learning model. Deep learning means that you have several layers of neural networks. So you have the input, as you can see on the left, and the output on the right, but then inside you have several layers of neural networks that make them that make connections without sort of automatically without the user interface. And to classify the quality of different algorithms, the standard technique is to look at the area under the curve of the receiver operating characteristic curve, which is the typical term to classify, to characterize how good is the algorithm. So the better, the higher the area under the curve, the better is the algorithm. So now, because the planets are so rare in the data, basically most of the stars don't have detectable planets with the transiting methods. They may have planets, but they're not detected. So we look at it as an anomaly detection. So in addition to, so that is the algorithm that Theta Ray has developed. So it's a fusion of algorithms that aimed at anomaly detection. It's used in various other fields, in finance, in the internet data security, and so on. But here it is applied to an astrophysical data set. So the most well-known sort of anomaly detection algorithm that is in public domain is the isolation forest. Okay, where basically this algorithm looks at the anomalies and characterizes the anomalies themselves, not looking at and doesn't characterize the average data. It looks at the anomaly specifically. And the Theta Ray algorithm basically improves on that, as demonstrated by these two plots that you can see. So it does improve the false positive by a factor of 3 compared to isolation forest, and the true positives are improved by a factor of 2. So an important thing to say is that the method that we use in this study is unsupervised. So that means we don't provide the characteristic in the data set of the, we don't label the data. We don't tell the algorithm which data is what it is. Okay, so the labeling is automatic. Okay, so there were several algorithms in this approach that the Theta Ray has developed, and one of them is the NY algorithm. So basically, it uses diffusion maps methodology, and it's primarily nonlinear dimension reduction process. So what happens is that if you look at the data as a very large matrix and you start to play with this matrix, it is very difficult to work with the full dimensionality of the matrix because of the huge size. So what this method does, basically, in a simple sentence, is it reduces the dimensionality of the matrix. Okay, and then the lower dimensional space basically determined automatically in a training phase, and that it makes it feasible to work with the reduced matrix to identify the anomalies and to use it for classification. Okay, so this is just a briefly flow chart that shows how the training and detection interact. So you have the input data, the higher dimensional data, and then you reduce the data here, and then you get detect the anomaly in the reduced matrix. Okay. So the other method, because it's a fusion of methods, the other method that was used was the randomized LU decomposition. So basically, because of these huge matrices that we get with the data, we need to again reduce the dimensionality, and one of the approaches is randomized LU decomposition as described by Shabbat et al. And it's basically builds a dictionary from the training data, and then each multidimensional data point that is not described by the dictionary is classified as anomalous data point. So this is another algorithm that is used to reduce the data. Okay, so there is more details on the randomized LU decomposition. Of course, I'm not expect you to follow, but the idea is, again, we have a very large matrix that we need to reduce to smaller manageable matrix that can be computationally feasible, and then it can be used to find those anomalies, which basically represent the transiting into exoplanets in our application. Okay, and this is another algorithm that is used, the Autoencoder algorithm. This is again an unsupervised machine learning tool, and it generates models of the data after a distribution of modeling of example data. So basically, it takes our training set and then makes some sample data that can be used then in the other algorithms to study the parameters and find the likelihood of reconstructing the data, basically find the likelihood that this is what we observe is a transiting exoplanet. So we can compare the original sample with the reconstructed generated data, and we can calculate a similarity score that enables to detect the anomalies. Okay, so here is an example from our study of training using the Kepler data. So the novelty of the approach is that we took Kepler data for training. Basically, the study was started when there were very few known planets for TESS. It was just launched. As you can see, the number of planets exploded exponentially. But when we started the study, we used the Kepler data to train the algorithm. And these are some results of the Kepler data. This is the heat map that shows sort of the correlation between the various parameters. Now, because it is unsupervised, unlabeled data, okay, we don't really care if the data, basically in some cases, it may have just not obvious physical meaning, like signal to noise level in various in planets. Okay, so when you're talking about signal to noise, it's basically a statistical feature. It's not physical feature of our planetary system, but still, because it's unlabeled data, all the data were used to train the algorithm. And you can see the difference in the between the planet and not a planet in the various parameters as they're marked in these four panels. Okay, so basically, now that we trained our algorithm on Kepler data, we can describe the effectiveness of the algorithm on 15,737 data points. So false negative detection was 2.5%. So that was, so the true positive were 2,883, the false positive 52, and you can get these area under the curve was above 0.9. So that means that this algorithm worked quite well when applied to Kepler data, where we had known exoplanets, so we could test it against existing exoplanets list. So with TESS data, we applied the data, and we got as well about initially we got about 100 candidates. Then out of about 11,000 light curves of TCAs, and then we could manually vet the small number because we only had about 100. And what we found is that there were some obvious cases where these cases could be removed from the data. And then we prepared a table here that shows the various cases where TICID is the test input catalog of the stars, and then the disposition. So many of the cases were known planet candidates, were TOIs that were already listed in the database. So on one hand, it would say that we would expect to just find new cases, but also we're glad to see that the algorithm identified existing TOIs. There are, of course, some false positives, like as you can see in the table, a transit here, and some off-target cases, or a single transit, and so on. So, or there is a case where there was a signal due to an asteroid in the solar system passing near the target star, affecting the background light subtraction. So there could be cases that would be very difficult to exclude a priori. And this is the table. So you can see some disposition of all these cases. Some of them were known planets, like the WASP 71b and 142b, and so on. So you can see that the algorithm, the unsupervised algorithm, was able to identify quite a few valid planets and TOIs, as well as 3 cases that of new planetary candidates. So using these 11,000 light curves, we were able to identify also 3 cases of new planet candidates. And here are some graphs that show the light curves of these planets, as you can see, as they were identified by the algorithm. So just to show you the types of local view light curves that we see. So you can see this on the left is the known planet, on the right is the new planet candidate, and TC period is the planetary radius. This one is 5.8 Earth radii. This is 2.37. This is the period. The period here is very short, and this is the depth normalized units. So there is another case, again, identified by the algorithm of a known planet, and then an example here of new planet candidates of 4.9 Earth radii. So, and you can see that the period is about 22 days. So now, some more examples. So you can see these 2 is the new planet candidates you can see here, and one of them is the below 4 Earth radii. So that would be sort of, I don't know, the period is quite short, but it depends on several parameters. But definitely the radius is what we would expect or would like to have for habitable exoplanet. And these are the known planet candidates, for example, with similar variability. So you can see that these types of shapes of light curves are very difficult to identify when you have a large number of these curves, but the algorithm was successful identifying several new cases. So just to summarize, okay, so we have the search of exoplanets, as you all know, is a new and exciting field with 5,000, more than 5,000 confirmed exoplanets at this point. And we basically applied the Theta Ray fusion of algorithms of semi-supervised and unsupervised machine learning methods and demonstrated using TESS TC data that we could identify exoplanets as well as new exoplanet candidates. So we had 50 exoplanetary candidates were uncovered, and from these, with manual vetting, we further found that 3 of them are new candidates that were not identified before. So this algorithm is sort of complementary to supervised methods that are maybe more efficient, but they also are not 100%. And because we are dealing with very large data sets, that even if a few percents are missed, if we have a different approach, a complementary approach, like the present method, it can yield additional planets that were missed by other algorithms. So that is sort of the usefulness of having another tool that can be applied sort of in an orthogonal way to other methods. In particular, the one we use that is focused on mathematical techniques that search for anomalies, and that produces promising result, as demonstrated in our published paper. And that's it. Thank you very much.
Thank you so much, Leon. That was a really great talk. I have a few questions, but I see we have a hand up in chat. So go ahead.
Hi, yes, thank you for this so interesting talk. So I just have 2 questions, if I may. So the one, could you possibly explain a bit more the difference between the global and the local training, which you mentioned early in the talk, just because I'm a non-expert?
Yes, the global view, that means when you look at the light curve, okay, maybe this one shows this better. So on the left, we see the time series of the flux, okay, and we see that there are dips, okay.
Yeah.
So that is the full data set, okay, with all the points. Now, let's say we take each of these dips and combine them together by limiting to some hours from the mid-transit. Here it's like 10 hours left and right, okay?
So would you normalize them to their deepest level, for example, when you combine them?
For example, yes. Yeah, there is a fit that they're doing, is a least square box fit, okay? So then you can normalize them and fuse them together, and then it gives you your local view. So that will reduce your signal, increase your signal to noise. Basically, the signal will become stronger because you're combining several of these transits together. And you're focusing on a time that is close to the transit rather than looking at the whole or larger time series. Right. Okay, so this is like a larger time series of days, okay, and this is hours.
I see, yes. And the other question is, you mentioned that when you did the training with the Kepler data, the data that you used was, you had very little data when you did that training. So I'm just wondering if when you had little data that you used for the training, you used a limited amount of data to do the training. And
Yeah,
I'm just
no, we
wondering
used,
if that
yeah.
amount, if these data might bias the result in some way, if they have some, there are some systematics that are characteristic of this small subset. And in which case, wouldn't you want to do some iterative retraining as you get more and more data, including other methods, to improve the results and false positives and so on and so forth?
Yes, it's possible that the training has an effect on the results, of course. I think you misunderstood our point. I mentioned that the Shalot and Vandenberg, they use the small subset.
Oh, okay.
We used a different, yes. We used a different satellite, so that was even more sort of daring,
Okay.
if you may say.
Okay,
so we
yes,
used
yes. This
Kepler
refers
data.
to them, yes, yes.
Yes, yeah. We used Kepler data to train the algorithm and then apply the algorithm on test data. Okay, because
Okay,
at that
great.
point, there were not that many exoplanets from test data when we started the study. But of course, you can improve these methods by, eventually you want to automate the process. So the training is a step, but because it's machine learning, right? So you would expect that the algorithm learns automatically and improves the result, right? So the training is one part, but then the machine learning and how you apply the neural networks and how many layers you have and so on, they can have effect on the result that would be maybe more important than training, and that would be demonstrated by these AOC curves. Okay, so
Right.
that would imply, for different algorithms, your AOC curve can be better or closer to, high. There's more area under the curve for the blue than the red. So that means you have less false positive. And that depends on the details of the algorithm, not on the initial training.
Mm-hmm. Thank you.
Okay.
Thank
You're
you.
welcome.
Yeah, and I see Patty has her hand up, but if anyone else has any other questions, feel free to raise your hand or you can post them in chat, but go ahead, Patty.
Hi, thank you, Leon. Great talk.
Hi. Thank
I
you.
have a couple comments and a question. So I'll start with the question and making sure I understood what you're focusing on. Are you starting from light curves that have already shown threshold crossing events and then sifting through those to look for new planets that the current methods don't find, or are you starting from a larger set of light curves?
Oh, Leon, I think you might have muted yourself.
Sorry. Yeah, we start with threshold crossing events.
Okay.
And
Go ahead.
they're already, for example, when we did the study, we had nearly 11,000 threshold crossing events already.
Okay,
so out
so
of 200, yeah.
So your goals are to basically take a look at, those starting from like, say, the 15,000 that you showed in the example, how many pretty confident, how many high confidence planets are in that data set that the current methods may have missed? That's
Yes.
the goal. Okay.
Yes. Well, the goal is to identify exoplanets, but because we're using algorithm that is sort of different from what is used by other methods, then we hope to find those that are missed by other approaches.
Mm-hmm. Okay, very cool. And then the comments I had, I actually sent you a couple links while you were speaking. There are a couple efforts underway within the TESS team right now to do something similar. And one of them is at NASA Ames. The folks involved in that are the folks that run the pipeline, and they're using a machine learning algorithm. There's an article about it that I sent you. And then there's an effort underway at Goddard that involves a whole bunch of folks that are looking at developing their own light curves from full frame images and doing a similar search. So I popped a link to you on that as well, just
Yes,
to
I
make
will
you
take
aware
a
of
look.
those folks,
you.
and maybe you guys can
Thank
talk
you.
to each other and compare notes.
Thank you. Yes, that would be very interesting, of course, to see. The one aspect of the study is that the algorithm that was applied here is a commercial algorithm. So it's available. I mean, it's not in public domain. So it would be the same as, for example, people use Mathematica or Ideal. So if so, it would be difficult to apply this to cases without, having collaboration from people in this company, or having that algorithm or software purchased by some institution. But I would, that's sort of, from the science point of view, it's a limitation of the availability. Yes.
That's a good point. We also saw in the Kepler and K2 days that, groups that had their own like independent methods of finding planets, it was like a Venn diagram of overlap of which planets were found by multiple methods. And there's also some interesting distinctions between the various methods as well. So it's a cool area of study. Thank you.
Thank you.
Thanks, Patty. Does anyone else have any other questions for Leon? I have one. It's probably a pretty naive one. This isn't my field of expertise, but I was just wondering, I can tell from your presentation that this particular algorithm and the methods that you're working with are focused on photometry, but where's the field at? Where's the machine learning field at when it comes to spectroscopy? Are there folks working on trying to pick out certain elements from really good, you probably need a really good signal to noise. So, looking ahead to James Webb, like are folks looking at using machine learning in that realm? Do you know of that?
Well, I'm not specifically aware of these efforts, but I can tell you that in solar, that is my main sort of field of expertise, the machine learning being used to analyze the spectral images as well, or narrow band images. Maybe it's less useful for stellar application because there's more imaging information. But I don't see a priori any reason why not to use a machine learning method when you have a large data set and you want to find some properties of this data set that would be sort of impossible to do manually. So definitely, if there is a large data set of spectral features and you want to identify some properties, classify according to these properties, then definitely machine learning is a good approach for classification of large data sets.
That's cool to hear. I'm curious if folks are working on that in the background somewhere. Does anyone else have any other questions for our speaker? If not, we can end a little early. If you do have any questions, feel free to message me and I can get you in touch with Leon. But Leon, thank you again so much for coming out and speaking with us today. It's really interesting work you're doing.
Thank you very much. It was a pleasure.
All right. Well, have a good day. Take care, everyone.
Bye-bye. Thank you.
Thank you.